Okay, so this is Math 313, Lecture 27. I apologize if I seem a little bit more tired than usual. I was up till about 6 o'clock last night trying to get the Mathematica code to work. I've done this in previous years in C. Mathematica did not like it unless I changed things to local variables rather than global variables, even though I kept clearing things. I don't understand why it works, but it works. And at this point, it's 6 in the morning. I'm just glad that it finally works. All right, so the 3x+1 problem, we've talked about how difficult this is. So an plus 1 is either 3an plus 1 if an is odd, an over 2 if an is even. Okay? So we want to make some conjectures about this. Okay? So I think we've done one conjecture already. So the first one is for any seed a0, there exists an n such that an equals 1. You eventually iterate down to 1. There's a weaker conjecture which immediately implies this. So I'll call this conjecture 1 prime. For any starting seed, there exists an n such that, what do you think is a weaker conjecture but is essentially equivalent? I mean, yes?
It falls into a cycle.
So one possibility is it could fall into a cycle. So in some sense, this is assuming that there is no cycle. Right? This is saying that eventually you iterate down to 1. There's a weaker condition that will imply this. So instead of iterating all the way down to 1, what do I assume? At some point I iterate to
Something less than what you started?
yes, something less than I started, such that an is less than a0. At some point in time, I'm at a smaller value than I started. And then as long as that's true, it's the lather, rinse, repeat method of mathematics, right? Once you iterate at some point in time and you're smaller than when you started, well then you use that as your new starting seed, and at some point. Both of these conjectures, well, I'm sorry, the second conjecture is technically false. What do I have to do to fix the second conjecture?
Can't start at 1.
Yeah, I can't start at 1. For all a0 not equal to 1, you will eventually get smaller. If I start at 1, I'm not going to get smaller. Okay? Other than that, no matter where I start, I will eventually get smaller, and that will imply. Anybody come up with any other conjectures? Almost surely whatever you conjecture, I will not be able to prove.
Well, for any number
Okay.
greater than 2,
Okay.
we will have at least 2 steps to get to 1.
Okay. So one thing could be the number of steps. For all a0, you said greater than 2 or not equal to 2?
Is it greater than 2?
All right, greater than 2. Need at least 2 steps.
Because if it's 2, it's just 1 step.
Right. Now, of course, in some sense, this is a bad definition to use if we want to iterate down quickly. Because as your number is higher and higher and higher, the best case is I keep pulling out a 2 every single time. And so the number of steps I need is going to have to grow with the size of the number. So we could look at the related map. Let's see if this moves just am I in focus here?
Yes.
Okay, bn plus 1 equals 3bn plus 1 over 2 to the L, where 2 to the L is the highest value that divides 3bn plus 1. So I could pull out all the powers of 2 at once. If I do that, would this conjecture be true for b? No. Because if I hit a huge power of 2, boom. But of course, I can't start at a power of 2. I have to start at an odd number. But I could start, so here's the question. Let's say I want 3x plus 1 to equal 2 to a huge power. Then that would mean 3x equals 2 to the L minus 1. So I want x to be 2 to the L minus 1 over 3. So all the time we've spent doing congruences is now going to pay some dividends. Is it possible for 2 to the L minus 1 to be a multiple of 3? And if so, for what values of L? So give me one value of L that works. 2. So then I would get 4 minus 1, which is 3. And then I should be able to get an arithmetic progression, right? So what would I have to add? I want 2 to a power to be 1 mod 3. So I'm not going to change the congruence. So what would be the next? So L equals 2 works. 4 works. You know, what works up to 4? 6, 8. And the reason is because 2 squared is 4, which is 1 mod 3. So every time I increase L by 2, I'm not changing the residue class of 2 to the L. So I have an infinite chain of things. And so for all of these things, it will take me one step in the B map to iterate down to 1. But it would take roughly L steps if I take the older map. So this leads to an interesting question about how long will it take. So there is a difference between the two. All right, so probably over here would be fine. So let's say we do the A map. So let's start off with x equals 2 to the L minus 1 over 3. How many steps does it take to iterate down? Is it L steps? I think it's L plus 1. I first multiply by 3 and add 1, and then I have to drop L times. So I think it takes L plus 1 steps. So it takes L or L plus 1 steps. I really don't care about the difference between L and L plus 1. I'm just trying to get a sense. How would you compare L to X? What's the right comparison? I want to try to figure out what's the right scale to study this. Logarithmic. What base should I take the log? Yeah. So if I look at the log base 2 of x, this is going to be the log base 2 of a third plus the log base 2 of 2 to the L minus 1. And then this is if L is huge, the log of 2 to the L minus 1 is approximately the log of 2 to the L. That's going to be L. If you wanted to estimate this, if you want to do it exactly, it's going to be the log base 2 of a third plus the log base 2 of 2 to the L plus the log base 2. I've pulled out a 2 to the L, so we get a 1 minus 1 over 2 to the L. 1 minus 1 over 2 to the L. And now if I wanted to use like a Taylor series, can I say the log of 1 minus x is about x? Can I use the Taylor series that the log of 1 minus x is about x? Yes or no? Yes?
I think you can, right?
I mean, the log of 1 minus x, the Taylor series is, negative x minus x squared over 2. And if this is a very small number, the square is going to be very small, right? Why can't I use the Taylor series expansion for the log? Be really paying attention to what I'm writing on the board. Yeah. It's not, I have log base 2. I have the Taylor series expansion for the log base e. I would have to have a multiplicative conversion factor. Fine. Not a big deal. I'll have like a log of 3 base 2, a log of 2 base 3, something like that. This is going to be of size 1 over 2 to the L. And so this is going to be approximately equal to L plus a small constant. So you want to know how many steps it takes. It looks like a really good thing is on the order of the log of x, base 2. Do you think, in general, it's going to be faster or slower than this for a typical x? slower. Why?
Because this is basically the ideal case for you.
Yeah.
You start decreasing.
This is the ideal case. The best possibility, if I want to get down to 1 as fast as possible, is pull out 2's every single time. Every time I go up, I then have to go down. If I go up twice, approximately how much have I gone up? Factor of 9. So for every 2 steps up, it's going to take at least how many steps to go down? At least 3. Okay? And so given the fact that we would expect it to go up occasionally, what's the right estimate? How long do you think it's going to take? This is a lower bound. This is not an upper bound. Right? So the question is this the right order of magnitude, or is this completely misleading? Let's look at another problem. What's one of our favorite arithmetic functions we've looked at? We've used this function several times. It occurred in RSA. No. Yeah, we needed a nice multiplicative function. We used it in RSA. Yeah, the Euler Totient, right? So, phi of n is the number of integers m, 1 less than equal to m less than or equal to n, with m and n equals 1. This was a really good function. Another good function, I think, we had the divisor function. This was equal to the number of m, 1 less than equal to m less than equal to n, m divides n. And we had the Mobius function. This is equal to -1 to the r if n is a product of r distinct primes and 0 otherwise. These were 3 very nice functions. The Mobius function, it's plus or minus 1, oscillates wildly. This is bounded. Okay. Phi of n, we've talked a little bit about how large and how small it can be. The divisor function can be extremely small. For large values, what's the smallest the divisor function might be? Yeah. So note, the divisor function of a prime is 2. And then we could have a number which was a product of distinct primes, a primorial. And we could have on the order of like log or log, I forget which, probably log of the number. No, it's going to be much worse. Because it's going to be the number of divisors and not just the number of factors. So we could have a huge number of divisors of a number. So there's a huge fluctuation between this and maybe I'll call it the divisor of like a primorial. And the danger here is that by looking at this function at very special values, we get a completely incorrect vision of the true order of magnitude, the true growth of this function. It's varying wildly. Other functions, maybe the totient function, it varies, but maybe it doesn't vary by such as extreme powers. So the question is, how would we investigate 3x plus 1? So part of this class is attacking a new problem, figuring out how to conjecture and how to gather data to support your conjecture. We want to get data, right? We showed some functions last time. So what I will do now is I want to talk a little bit about the theory of computation of 3x plus 1. How many of you have ever watched Star Trek? Or even taken a class in it? Right? When I was young, my favorite part of Star Trek was the phasers, the photon torpedoes, and the engines. I now realize that was the ignorance of youth. The best part of Star Trek is they just talk to the computer and it programs itself and it does all the calculations they need and they go to the holodeck and play. And they'd say, computer, analyze all Bajorn anomalies for the past 10,000 years. Working. Will take 6 hours. Okay, let's go play baseball. And I know some people have to go play baseball soon, so I thought a DS9 reference would be appropriate. It's wonderful. They don't have to sit down and do coding. They just speak, and the computer self-programs. It's wonderful. Is the 3x+1 problem difficult to implement? In theory. No. If the number's odd, multiply by 3 and add 1. If it's even, divide by 2. These are trivial operations. How would you do this on a computer? We need to gather data. So how many of you have programmed extensively? All right. So what kind of language would you like to use for this? Mathematica is not a good one. I will show you Mathematica later. When I did my paper on this years ago, I used either C or C++. Okay. So if you want to use C, we are just dealing with integers. So you want to do things with integer classes?
Sure.
All right. So what's the integer class in C? Int. We have int. And then you have long int. Or is it just long, or is it long int? It's been so long since I programmed in C.
Yeah, probably it's long in Java.
Okay.
Try long.
Okay, probably long.
Try a long too.
Okay, so probably a long. Does it keep going?
You can implement. I mean, using those, you can make bigger.
You can make bigger and bigger numbers. It gets a little bit annoying. But if you want to just work with the numbers, you have to worry about the computer keeping all the numbers and all the digits.
You could use bit shifting operations to make the dividing by 2 really easy.
Okay, so how would you do the bit shifting?
You'd shift until an XOR with 1 comes out 0.
So what base are you doing this problem in?
Fine.
Yeah, this is actually much better to do in binary. Because in binary, when you're dividing by 2, you just shift everything to the right. So the 3x+1 problem, if you're going to implement it, you should actually program it in binary. And in fact, if you now want to do 3x+1, the addition is very easy in binary. 2x is just a shift. You just append a 0 at the end. And then you can just put an x underneath it, and then just do addition like this. So this is really a problem to work on in base 2. I will keep doing it in base 10, although the code I've written actually has a function in it that allows you to change the base if you want. The best way I know how to work with this is you could keep creating subclasses of numbers. So for instance, I could move down in blocks. And maybe this is a long, and then this is a long, and then this is a long. So maybe something like this. This is long times 10 to whatever the length this is, maybe 5. And then this would be long times 10 to the 10, long times 10 to the 15. Just match it down and then define a procedure to work with all of this. There's a nice simple way to do this. It's to work with a list or to work with an array. So if I work with an array, what am I doing? I'm adding 1, I'm multiplying by 3, I'm dividing by 2. If I do this as a long list or array, and I'll show you how to do this in a moment, it's not that bad.
Depending on implementation.
Depending on implementation. But the advantage of this is I never have to work with a huge number. I only have to store a massive list in memory or a massive array in memory. And then if I have an array, I just have to add 1. Well, if I add 1, I just keep propagating down. If I multiply by 3, I multiply by 3 and I keep propagating down. That's not so hard. The problem is if I'm doing things base 10, how do I divide by 2? And then you got to start at the beginning and go through all that crap. Anybody know the good way to divide by 2 base 10? Yes.
Take the digit, divide that by 2, and if the digit before it is odd, add 5.
So I could start doing something like that, but that's getting painful. Why is it so nice to divide by 2 in binary? You just shift, right? Wouldn't it be wonderful if instead of dividing by 2, we divided by, what would we like to divide by in base 10? 10. So what should I do to convert this so that I can divide by 10? It's a nice programming trick.
Oh, multiply that.
Multiply by 5 and then divide by 10. So the best way to divide by 2 base 10 is multiply by 5 and then just shift everything down. And then I don't have to worry about, encoding, carrying, and all those operations. Okay. Can you hit the mute button? Okay. Can you hit the laptop button? Sorry, I guess I didn't hit the laptop button earlier. And maybe the laptop button is on the left. Yeah, try that one. I think that's the laptop button. Okay. Is it showing on the iPad right now the code? Because it did not
It's washed out.
It's washed out.
Maybe the lights are off.
Let me try the lights. But it was recording earlier, which is what was.
Now it's like faintly outlined, but you can't really see it.
I mean, this is incredible. Apologies for this. It was recording at the beginning.
Maybe in that screen, just tap on it, see if it'll.
Had it for 1 second. I'll try for just like a minute or two. If it doesn't work, then we'll go to plan B.
Wonder if turning the computer brightness down.
I can try that. Okay, so that just changes it on my screen. Is there a brightness over there? All right, so
Yeah.
let's see if this works. Do you have an idea?
Oh, I have a pair of sunglasses. We could put it in front of the projector.
Try it. Does anybody have like a couple of pennies or? Let me try business cards. I've got to prop up this so that it. See, it's strange. In previous times, all throughout the semester, it's recorded no problem. For some strange reason, it did not like recording last time. So.
I have faith in
So
Oh, what if you put the projector screen up and just project it on the blackboard?
on Blackboard, you can try that. All right. Is this showing up in the recording? All right. All right. Good idea. That's fine. That's fine. But you can see the rest. All right. So, amazingly, people think the hardest part of the problem is the coding. It's actually projecting it onto a screen. All right. So I'm going to just show a little bit of the code from last time. Let me just change the height of this. So
Good.
we'll change the height of this one. Okay. All right, so now here was the old 3x plus 1 problem from before. We had our function f and g. F was, if x is even, we divide by 2. If it's odd, we add 1. G was just a little bit better. We assume that the input, or this should not be an even number, we should assume the input is a odd number, right? And then if it was odd, we multiply by 3 and add 1, and then we just keep removing powers of 2. That was the while loop. And so the g just does everything all at once. We had our iterate function, which we put in a starting value, and we have our print option. We start the count at 0. The current value is whatever we're starting with. We print where we start, and then while the current value is greater than 1, so we're essentially assuming the 3x plus 1 conjecture as we code, which is fine, but you can always put in a little extra condition just to make sure. Maybe if count ever reaches 1 million, print I'm tired, I'm done, something like that. So we just have our new value is the iterate of our current value, increase the count by 1, and then if we want to just print out the path, if print equals 1, we'll print the current value. And so the code really isn't that bad. So the next one, I don't think we did this entirely in class. So now iterate function range. So I'm going to do something num_do times. I'm going to start at a high power of 10, and I'm going to choose which function I want to use. So if the function value is 1, I'm going to use f. If the function value is anything else, I'm going to use g and just dump down immediately. I'm going to save things into the result file. The longer your list is, the more Mathematica slows down a little bit. But if we are doing a lot of calculations, if we're looking at a huge number of numbers, the size of the list is going to be insignificant in terms of slowing things down. So I start the count at 0. I know the baseball people, good luck, travel well. The current value is just the random integer 10 to the start power. So I'm going to randomly choose a number. It is possible that I could choose a number that's significantly less than 10 to the start power. Maybe start power is 100. So I'm randomly choosing a number from 0 to 10 to the 100, and I might get the number 15, which is significantly smaller, many orders of magnitude smaller. Do I have to really worry about that possibility? No. What's the possibility that I am less than 2 orders of magnitude? I'm sorry, that I'm more than 2 orders of magnitude below? At most 1%. The probability that I'm at most 4 orders of magnitude, 1 over 10,000. So with extremely high likelihood, I'm going to be within 4 orders of magnitude of 10 to the start power. And so what I'm going to do is the following. So n goes from 1 to num_do, so how many iterations I want to do, I'm going to do that. Count is equal to 0, and then while current is greater than 1, I iterate, and I increase the count by 1. And then when this while loop finishes, I've iterated down to 1, so I now store that result, that value of count, into my results list. And then I move on and I do this for the next value of n, and I keep doing this. All right, and so I now have a couple of output things. I write how many iterations we're doing, and I write where we're starting. I write what the average value is. I write what the standard deviation is, and then I print a histogram. And so here, I was doing 100,000 iterations starting at 10 to the 1,000. So this is a 1,000-digit number. Years ago when I was using C, I was able to do, I think, 10,000 to 100,000 digit numbers without too much trouble. Timing is a wonderful command in Mathematica. If you put timing around something, it tells you, not surprisingly, how long it took to do it. And so this took 6,542 seconds. So there's 3,600 seconds in an hour, so this is around 1.8 hours. What does that plot look like? Yeah, it looks like a Gaussian. What's the most important quantity related to this Gaussian, or the two most important quantities? The mean and the standard deviation, right? What's the average value? Looks like ballpark about 8,000. And what's the standard deviation? Maybe on the order of 300-400. And if I look at it, the average was 8,003, and the standard deviation was 304. Do you think the average is exactly 8,000? Yeah, this could be maybe some numerical fluctuations. Do you think it should be exactly 8,000? Or do you think these are just really lucky choices of numbers? Seems a little bit lucky. So what we would love to do is we would love to figure out what is the true decay rate. So now I think I can open up even a new window. I'll move this down. So we want to look at the log of our number, which was 10 to the 1,000. I always forget in Mathematica how you do things. I think you do the base first and the number second. Okay, yes. Okay, people can still see this? Okay, I'll make it a little bit larger. Okay, so if I now do log, we said maybe base 2, and our number we're doing was 10 to the 1,000. And the reason we get this is because Mathematica is doing the result exactly. If I don't want it exactly, I can just put a decimal point anywhere, and that will approximate things. 3,321. That's much less than 8,000. Are we surprised that it's much less than 8,000? Okay, why aren't we surprised?
So it has 1,000 powers of 2 in it.
Okay, so
So that could, it seems like it should make it go faster. Maybe not.
well, but we just got maybe the log of x has to be at least. So the number of steps has to be at least the log of x. So over here, when we take our number 10 to the 1,000, we are getting 3,321, and we were actually getting 8,000. Yes.
Were we using the method that counts each division of 2 as a thing, or were we?
So that's a good question. So here we are using the option 2. So all the steps of 2 count as 1. So now are you surprised?
It's still on a similar order of magnitude.
It's on a similar order of magnitude, but what we want to do is we want to get a real sense of what the order of magnitude is. So I'm going to explain to you in a moment how to do that. I want to just briefly show the other code. So here's how I did it. There's better ways of doing this. This is how to do everything completely as a list. I'm going to have something called initialize length, base, and factor. Base will either be base 2 or base 10. I'll do base 10 just for us. The factor is because I want to just be a little bit crude with my coding. When I start doing these operations, is it possible that the number of digits could change? Yes, right? If I'm multiplying by 3, my number could add 1 more digit. This is very wasteful. What I'm going to do is if I want to look at a number with 4 digits, I'm going to maybe choose my factor to be 2, and I will set aside 8 digits. And I'll just assume my number is never going to increase by more than a factor of doubling the number of digits. What you could do to do a better job dynamically managing is to just say, well, look, I'm going to have my list, and at most I can add maybe 1 more digit as I do my 3x+1 maps. And that would save a lot of time by not having to look at such large lists. I'm just doing this to be safe and just make the programming a little bit faster. So what I now do is my initial value of a is going to be a random integer. I choose a number from basically 0 to half the base. Then I multiply by 2 and I add 1. This just forces my last digit to be odd. I don't want to start off with an even number, just so that I know I will initially be multiplying by 3. And then I'm going to choose my length from length plus 1 all the way up to factor times length. I'm going to just pad it with zeros, just to be safe. Here is a very simple way to just add 1. I initialize carry to be 1. And what cost me several hours last night was I have to have this as a local variable. It didn't like it when the same procedures were using things even though I cleared them. So I'm going to have a output is local, only the add procedure sees it. I initialize carry to be 1. I create something called new. and then I initialize everything in new to be 0. So I read in a number, and now what I do is I start off at 1 and I go all the way up to how big my numbers are, and I take my number and I add carry. And then if I'm greater than the base, my new number, if I'm less than the base, my digit is just going to be that sum, and now my carry is 0. If I'm greater than the base, greater than or equal to the base, then I subtract base from x, because when I'm adding two numbers, I can't be more than the base higher. And now it carries back to 1. And this allows me to just march down and add things as a list. And then the rest is just some outputting stuff. If I want to multiply, I read in a number called m number for multiplying. I put in the fact I want to multiply by, maybe it's 3, maybe it's 2, maybe it's 5. Those are the numbers we really need. I put in the length, the factor, and the base. And now what I do is I initialize my new number to be 0 again. You could probably skip a lot of these steps. I wanted to be very safe because it kept not working. And then I just march down and I take my number, I take the digit, I multiply by my factor, and then I add my carry. Initially carry is 0. And then if my new number is less than the base, then the new digit is just that number. And if it's greater than the base, then what I do is I look at the remainder of my product with the base, call that y. The new digit is just y, and now the amount I carry is the product minus the remainder divided by the base. And then I just march down. So it's really not that hard to put in your own multiplication procedure on lists. The shift procedure is really nice. You just shift all the digits down by 1. I put in a little print routine to just print out, make a list and print things out. I put in a little value routine, find the value of the number. And then here's a little procedure. We'll see how long it takes. Probably helps to actually compile all the functions. Okay. Initialize was in a different line, sorry. All right. All right, and so for instance, here is my string. I'm using things with 10 digits, so I'm going to work with 20 digits to be safe. Here's my initial number. It starts odd. I now just write it over here in base 10 so you can see what the number is. And then I start I did a couple of operations. I think multiply by, the first one I did was I printed my number. I multiplied by 3, and then I added 1. So if you look over here, if I multiply 9 by 3, it's 27, carry the 2. You can see everything is working. I then added 1. I then divided by 2. Okay. And then over here, just a code to just go through. It took me 779 steps to count down from 10 to the 100, or some number randomly chosen along there. And you can have things printing out as you go. Did I want to do this? Oh, this doesn't seem to have it as a procedure. All right, it's not a big deal. So this is how you would do things as a list. I will post the code. It takes a little bit of familiarity to become happy with these things. So over here, I've got print me as 0. I'll make print me be 1. I'll start off with a 4-digit number. And so you can see here's my number 6639. And it's odd, multiplies by 3, adds 1, divides by 2. And you can just see it just iterates everything down, and you can just see every single step. So half of 710 is 355. I multiply by 3 and add 1, and you can just see all the output. So you can work very easily with just long lists for something like this. And so you can investigate pretty high. Okay, any questions on?
I was just wondering, is this, I guess maybe not in mathematics, but in general, would this be quicker than the other programs we're using to evaluate?
For Mathematica, I think the other one was actually going a little bit faster than this, which I found surprising. But I think for things like C, you don't have to build a long structure. I think something like working with lists worked pretty well. But again, it's going to depend on the architecture of the system. the idea was to just show you, here's a very easy way to work with a 100,000 digit number. You don't have to worry about the different block structure. You don't have to worry about writing a complicated function to work with the different blocks and to carry. The carry and the shift operations aren't that bad. Okay. So now, let's go back over here. So here was our program. It does the count, and it returns this average value. We want to get a sense of how things change. So to get how things change, we would want to start off with a lot of different areas. So what I'm going to do is I'm going to just take this code, and I'm going to move it down, and I'll change this. Iterated range, analyze. So now we have a start power, and maybe we need to do num powers. Maybe we'll do 10 orders of magnitude and get some sense. All right, so results will be 0, and then power results will be empty. And now what we want to do is, this is our loop as before, and it's going to calculate all these things. And now, instead of printing out all these things, what we want to do is we want to save the average number of counts to our list. And we want to save the value we're at. So I'm going to have to add another loop for p equals 1, p less than equal to num powers, p plus plus, end of p loop. Okay? So now, what we do is, for each power, we're going to calculate a huge number of trials. And we're going to save that result to power results. So now we've finished the end loop, and now power results will be equal to append to power results. And now we want to save the count, but that's the y. The x value is going to be what we start with. So we're going all the way around 10 to the start power. So let's save that as our x coordinate. And maybe we'll call this 10 to the exponent. And so we'll do this as 10 to the exponent. And now, for each choice of p, exponent will equal maybe start power plus, maybe we'll go up by 10 exponents every single time, 10 times p. So maybe the first one we'll do maybe around 10 to the 10, then 10 to the 20, 10 to the 30, 10 to the 40, 10 to the 50. Does that seem reasonable? Do you expect to see a linear relationship? All right, so let's see. So now the last thing we would want to do is we would want to just print things out at the end. So maybe do list plot power results. One thing that's annoying is we actually have to tell it, list plot just makes a image. We want to print out the image. Okay, so now we're calling this, all right. So let's do 100 simulations because we don't have that much time. Let's start off at 10 to the 10. Let's do 10 powers. And then do we want to pull out all the powers of 2 or not pull out all the powers of 2? Pull them out, okay. Hopefully this works. And so this is, we're getting about 2 data points. So let's see. Oh, we don't want to put in count here. We want to put in the average, right? So what we could do is actually, if we just want the average, what we can do is at the start of the end loop, we set count to be 0. And then every time we go through, we increase count. So now all we would have to do is do count divided by the number of numbers we did. And that would be the average value. And it's just put that in as an integer. OK. So let's try going a little bit higher than just 10. OK, so right now it's getting the same number of things every single time, so we must be saving something incorrectly. So this is the end of the end loop. Oh. So I think now we would just do it over here, 1.0 count divided by numdo. OK. What are we doing wrong? So for each sort of n, we choose a random value. While current is greater than 1, we keep applying our function, we keep increasing the count, and then when we finish, we move on to the next number. And then when we finish this, we've got all of our counts. Something is wrong, because it's somebody help me quickly. Oh well, I will have to then fix this for tonight. For n, this is the end loop right here. And so over here, we keep increasing count by 1, and then when we finish, we add this to power results. And it's always adding the number 1. So
Do we want to do and of the exponent or just the exponent?
we could do things. I mean, this would be doing like a log plot. We could do something like this. And so here it's saying it's 1 every single time. So I will have to check and see what is wrong here. This is the problem of trying to do something live. But the idea is I will send this later, and we'll finish this on Monday in terms of just how we would analyze the data and what it would look like. And the idea is we'll look at it both as a regular plot and as a log plot and see if we can use that to sniff out the behavior, and then we will shift to elliptic curves. Okay.